In this video, I'm going to talk to you about momentum. Momentum is a word that we use in ordinary conversation. A sports announcer might talk about how a team is gaining momentum or has momentum as it's scoring points or winning a game. Or we talk about how an idea is gaining momentum, becoming more important or more popular. But today we're going to focus on what this means from a physics standpoint, which it does mean we have to talk about math. So if an object is in motion, it has momentum. This is a property of an object that is moving. We can think about momentum as being mass in motion. The magnitude or the amount of momentum is going to depend on then the mass of the object and the velocity of the object. Because momentum is a vector quantity, it's going to have both magnitude and a direction, and the direction is always going to match the direction of the motion. So it doesn't have a one-time with the motion and one-time against like we see with acceleration, but momentum is always going to be in the same direction as the motion. So because momentum is related to mass and velocity, and in fact, it's directly proportional to mass and velocity. As you increase mass, you increase momentum. As you increase velocity, you increase momentum. We can set this up in an equation using the letter P for momentum, saying that momentum is equal to mass times velocity. And since mass is usually given in the units of kilograms and velocity often in meters per second, not always, but often, then we end up with this unit for momentum as being kilograms times meters per second, or it's just usually just said kilogram meter per second. So let's just apply this formula where momentum is going to equal mass times velocity. If we have a 1,000-kilogram car that's moving northward at 20 meters per second, its momentum would be its mass times its velocity, or 1,000 times 20. So we end up with a momentum of 20,000 kilograms times meters per second, and it's moving northward. So we'd have to put that direction in our answer as well. So if momentum changes, that tells you that either the mass or the velocity has changed. And typically it's the velocity that's changing. And then if velocity changes, you already know that that means we have acceleration. And if we have acceleration, it has to be produced by a force. So when we're talking about momentum, we really need to talk about what's going on with force. But we need to add another component into this, because let's think about what happens with time and forces. If you have a force that you apply for a very short time, you're going to cause a short amount of acceleration, which will lead to a small change in momentum because you're going to have a small change in velocity because the force is not acting on that object very long. But if a force is applied for a long time, you have a large change in momentum. So when we're talking about momentum, we also have to consider the time that a force is acting on that object. When we apply this force over time, what we get is called an impulse. And the way we calculate impulse is basically using Newton's second law, but we're combining it with the formula that we have for acceleration. So we know that Newton's second law is force equals mass times acceleration, or a net force is the mass of the object times the acceleration. And we know that acceleration is the change in velocity over time. So that's where our time comes in. So basically, if we substitute the change in velocity over time for the A in the F equals ma of Newton's second law, and then multiply both sides by time, we get our force times the time, or our impulse, equaling the change in velocity times mass. And the change in velocity times mass, as I've said a few slides ago, is momentum. So impulse is actually equal to the change in momentum. Whatever is happening with your impulse is going to be equal to your change in momentum, but the number-wise, magnitude-wise, but the units will be different because, of course, your velocity would be meters per second, your mass unit would be kilograms, so momentum, again, as I said, is kilograms times meters per second. But your unit for force is newtons, and the units for time often are things like seconds or minutes. So we'll just use seconds because that tends to be common in physics problems. So impulse, the number would be given with the unit Newton seconds, and the momentum, the number or the magnitude, would be given for kilograms times meters per second. So let's apply some of these formulas. We've got a table here with a lot of spots missing. Let's take a look at how we can use these different formulas to do some calculations. So for starters, we know that the impulse and the momentum change is the same. So the impulse and the momentum change, these two columns here in the center, the numbers will be the same. So we've got a couple here we can just go ahead and fill in because those are already provided for us. We've got some others we have to calculate. And then our basic formula for momentum change was that momentum is equaling the mass times the velocity. So we've got a mass and a velocity here, mass of 10 kilograms, a velocity of -4. So we've multiplied those two together, mass times velocity, gives us a momentum, a change in momentum of -40. And again, I've got all the units written up here. We don't have the other values to do that same calculation in the other rows, so let's look at what other information we have. Well, since we know impulse and momentum are the same, we can go ahead and fill in this one as -40. So now we know that for this particular example in row 1, we have a mass of 10 kilograms, a velocity of -4 meters per second. Our momentum is a -40. Impulse is also a -40. We have a force that's going to be applied over 0.01 seconds. And so how much force is going to be needed? So then we're using the formula where force and time are involved. So this is our impulse. We're going to rearrange that because we're looking for force. And so we're going to put time on the other side. We'll divide both sides by time. So we're going to get our impulse, our big I, divided by time is going to equal our force. So if we take 40 and divide it by 0.01, we're going to get a force of a -4,000 newtons. So that was just rearranging this formula so that force becomes all by itself on one side just by moving time, by dividing both sides by time and moving it over. We can use that same formula to solve for row 2 because, again, we have impulse and we have time. And in this case, the time, instead of being 0.01 or 1/100th of a second, it's 0.1, which is 1/10 of a second. So it is a bigger number. It is a longer amount of time. And when you do the division, you find that the force needed then has gone down. It's only 400 instead of 4,000. So we can see from these two rows, from these first two rows, that force and time are inversely proportional. If you have more time, then it takes less force to cause the same change in momentum. And that becomes very important to how we apply this later on with something like automobile safety apparatus that we're going to talk about a little bit in class. So now we've got some other things that we need to fill in. Well, again, our third row, we've got a time, we've got a larger impulse, so it's not going to be the same number, but for an impulse of -200 newton seconds, if we again are having 0.01 seconds as our time, we can use this same formula where we have the impulse and the time to figure out our force, and this is going to be another force of -20,000, 20,000, if I get enough zeros there. And so we have a greater impulse. There's going to be a greater change in momentum happening, so we do need a greater force. So now all we have to do is finish filling in the change in velocity values for rows 2 and 3. So that can take us back to our momentum change formula, where the change in momentum is the mass times the velocity change, or the velocity change is going to then be momentum divided by mass. So we have our momentum of a -40 divided by our mass of 10, and so it's going to give us a velocity change of a -4 meters per second. Same thing is true for our third row, where we have a momentum of -200, a mass of 50, and that also gives us a velocity change of -4. So we can see from these two rows that we can have vastly different amounts of force applied. We have a -40 or -400 and a -20,000 because we have different amounts of masses. So the more massive something is, the more force is going to be needed to get to the same change in velocity. And I think you kind of know that intuitively because momentum is mass in motion, and when mass is in motion, it has inertia, or when any mass has inertia, and once the object is in motion, it's going to resist changing in motion. You'll have to apply more force to get it to stop or to change how fast it's going. So we have 2 more rows to fill in on this table, and we have all the information we need, because if you have any 2 values in the force, time, and impulse part of the problem, you can figure out the third. The same thing is true for, momentum, mass, and change in velocity, because we can just use algebra to rearrange equations. So on our 4th row, we're looking to figure out time. So we had already rearranged this first formula to give us how to figure out force, and we can do the same thing for time. So we would have that our time is going to be equal to our impulse divided then by our force. And in this case, our impulse is negative 200. Our force is negative 20,000. So that's going to give us a time of 0.010 seconds. So again, we're just plugging into those formulas and figuring out the math. Once we know our 2 out of the 3 variables, we can figure out the third one. So then to apply that 2 out of the 3 over here, we've got our momentum, we have our change in velocity, and so we've got our momentum equal to the mass times the velocity change. If we need to figure out the mass, we get our mass would be then equal to our momentum change, or P, divided by your velocity change. So that's negative 200 divided by a negative 8, which is going to give us a mass of 25 kilograms. So again, we're just using the formulas to calculate these values. And then finally, we have our last equation where we're trying to figure out, we're missing the impulse. We've got both the values for force and for time. And so impulse is just force times time, using this first formula exactly as written. And so negative 200 times 1, of course, gives you a negative 200. Somehow my pen does one right here. Negative 200 for impulse, which is equal to momentum. So we have a negative 200 for momentum. We know that velocity can be figured out by taking our momentum and dividing by mass. So 200 divided by 50 will give us, again, a negative 4 velocity change. So you will be doing these sorts of math problems. Hopefully you've taken some good notes on the slides, but of course we'll be practicing it in class. So let's talk about momentum and collisions. What's going on? Well, in a collision, the impulse experienced by an object, of course, is always going to be equal to the momentum change. That's just impulse equals momentum change. And the object is always going to speed up or slow down as a result of the collision. So let's look at these 2 collisions down here. We've got a tennis ball bouncing off the wall. So we have in case A, we have a tennis ball coming in with a velocity of 10 meters per second. And because we've got this is rightward velocity, this is going to be a positive 10 meters per second. And it's bouncing off the wall and then leaving at a velocity of 5 meters per second. And because it has now changed directions, it's going to be a negative 5 meters per second. So what has happened to the velocity? What is our change in velocity? Well, the change in velocity is going to be your final velocity minus your initial velocity. So that would be a negative 5 minus a 10, which gives us a change in velocity of a negative 15 meters per second. If we look at our case B, we have an incoming velocity of 30 meters per second and outgoing of 28. But again, remember, this is negative 28. So applying our formula to figure out the change in velocity, we're going to have a negative 28 minus 30 meters per second, which gives us a change in velocity of negative 58. And so case B has a greater change in velocity. We don't really have any other numbers here to work with, so we just have to talk in general. But if there is a greater velocity, that means there has been a greater acceleration happening to that object. And this greater change in velocity means there has been a greater momentum change. And since momentum and impulse are equal, it also means there was a greater impulse change or impulse applied to case B. So even though you think, bouncing is something that is slows you down if you bounce on a trampoline instead of just coming to a stop, the forces involved are actually rather high, because in order for something to hit, come to a stop and then rebound at such a high velocity, you have to apply a great force to that object. So collisions in which objects rebound, like we're seeing with this tennis ball, are known as elastic collisions. And elastic collisions where the outgoing speed is nearly identical to the incoming speed are conserving or maintaining both the kinetic energy, the energy of motion, and the momentum of the object. Because of that, they have a large velocity change. So we saw with our case B that we had an incoming velocity of 30 and outgoing velocity, or the velocity change was a negative 58 because you came in at 30 and went out at 28. And then because of that large velocity, it leads to a large momentum change, a large impulse, and a large force being applied. So the main point is when an object bounces, it experiences more force than if it sticks the landing. Let's look at a car crashing into a wall over here. So in our first case, it's coming in with a velocity of 5. It's leaving as a velocity of 4, which means our velocity change is going to be a negative 9. In the second case, it's coming in with a velocity of 5, but it has a 0 velocity at the end, so that the change in velocity is going to be a negative 5. So velocity change is greater in case A, so it's higher in A. Momentum then is going to be higher in A. Your impulse is going to be higher in A. And the force, assuming that your contact times are the same, will also be higher in A. Most of the cars today are designed to crumple when they're hitting the wall, and that is because that leads to a lower velocity change, and that is safer for the people in the car. So we've got a couple more examples here to finish up this video where we're applying these formulas that you saw a couple slides back. This formula, force times time equals change in velocity times mass, is known as the impulse momentum change theorem. And it just lets you think about what's happening with momentum, considering what's the force involved, how much time is involved, how does velocity change, and then, of course, we have to consider what the mass of the object is. And then when you're figuring out force, you can just rearrange that equation by moving time to the other side, dividing both sides by time. So we have Jennifer, who has a mass of 50 kilograms, riding along at 35 meters per second in her red sports car when she must suddenly slam on the brakes to avoid hitting a deer. She hits the airbag, which is why it's in the car, to bring her body to a stop in 0.5 seconds. So what average force does the seatbelt exert on her? Because, of course, that seatbelt is going to be what's holding her body back, but as it approaches the airbag. So our force is going to equal the change in velocity. So the final velocity would be 0, because she's going to come to a stop, minus the 35 meters per second that she is traveling at, multiplied by the mass. So her mass is 50 kilograms, so multiply by 50 kilograms, and then divide it by the time that this force is going to act, which is 0.5 seconds. And so in this case, if you do the math, you're going to get an answer of negative 3,500 newtons, because newtons will be what we're left over so far as units to give us for force, the unit for force. Compare that to if Jennifer had not been wearing her seatbelt and did not have an airbag. So then her velocity change is going to happen because the windshield is going to stop her head in a very short period of time. Instead of taking half a second to come to a stop, it's going to come in a stop in 2/1000ths of a second. So what would be the force then the windshield is going to exert on her head? Again, your change in velocity would be the same. You're going from 35 to 0, so we have a negative 35 for a change in velocity. Her mass has not changed, but the time has changed. So now we're going to divide by 0.002. And this is going to give us a whopping 875,000 newtons of force that would be applied by the windshield on her head. Of course, it's going to be negative. This is, math examples on why airbags and seatbelts are positive things in a car, because if you are being stopped slowly, which is what's happening in this case, the airbag is slowing down the time or expanding the time, giving you more time to come to a stop. The seatbelt stretches a little bit before it catches, so a little bit of time is involved before you are abruptly halted. Then the force needed to change your velocity from 35 meters per second to 0 is less than if you don't have those restraints and you crash into the windshield. And then finally, we have a hockey player who applies an average force of 80 newtons to a 0.25 kilogram hockey puck for a time of 0.1 seconds. Determine the impulse experienced by the hockey puck. Even though you have force and mass and time involved in this particular problem, this is one where you don't really need to think about mass, because the impulse is just going to equal the force times the time. And so our force is 80 and our time is 0.1. So it's going to end up with a force of 8 newtons being applied. And of course, it will be in a negative direction to stop the hockey puck. So even though this is just an example, you may have information in a word problem that you don't need to pay attention to. And then finally, as I just talked about in the airbag example, force and time are inversely proportional. So an object, if it has a momentum of 100 units, whatever those units might be, it needs an impulse of 100 units to stop. But do you do that in 1 second, where you have to apply a force of 100? Or do you do that in 10 seconds, where you apply a force of 10? Or do you take, 100 seconds and you only have to apply a force of 1? The amount of force on an object is inversely proportional to time. So to minimize the effect on the object that's experiencing this change in velocity, increase the time when a collision is involved. So to check for understanding, can you explain what gives an object momentum? It's moving. Can you calculate momentum from mass and velocity? Can you explain what is meant by impulse, force over time? Can you calculate impulse if you're given momentum and time? And then can you use this impulse momentum change theorem to talk about how velocity or acceleration or force or time are changing in a collision?